Example 1 here is going to illustrate that fundamental theorem of calculus. Evaluate f of x is equal to the definite integral from 0 to x of cosine of t with respect to t at a variety of x values. Why are they x values and not t values? Because x, those are the numbers that we're plugging into the function, which only changes the upper limit of integration, and that we're basically accumulating some area underneath the cosine function. Now, this is not one that we know, but somebody's done this for us, so I just have a series of pictures, and then from this series of pictures, we'll draw some sort of conclusion from it. So here's the first one. Let's say we're going to do it from 0. I think, though, we don't even need a picture for this one. If we go from 0 to 0 underneath the cosine function, we should have an area of 0, right? So here's the first one. Here's our first point. It's 0, 0. Right? Now I'm going to plug in a pi over 6. From 0 to pi over 6, what's the area underneath the cosine function? And it says that it's a half. Okay, now we're going to go from 0 to pi over 4 here. What's the area underneath the cosine function? It's root 2 over 2. Those numbers look sort of familiar. And let's do another couple. From 0 to pi over 3 for the upper limit underneath the cosine function, we get root 3 over 2. Look at those numbers, 1/2, root 2 over 2, root 3 over 2. Here, let's maybe graph these things. Okay, all right. So I'm going to make a little graph here. And this is a trig function. So I'm going to graph this as, okay, so there's 0, of course. We're going to say that this is pi, a 2 pi. You get a pi over 2, of course. And then here would be pi over 4. And on either side of that, you have your pi over 6 and your pi over 3. Okay, all right. And let's say that this one right there is 1. All right, switch your colors so it looks pretty. Maybe it should be pink. Okay, all right then. All right, so the first point there is 0, 0, put a dot. The next one is pi over 6. Pi over 6 is right here, and we're going to go up to a half. Half should be right about there. All right, and then the next one is at pi over 4, and it's root 2 over 2, which is about 0.7-ish. Why'd you turn out to be like a little line? I don't even know. All right, so there we go. It's totally accurate. And at pi over 3, we should have root 3 over 2, which is 0.866 business. I'll show this one here. So a little bit closer to 1. And then what do you think it's going to be at pi over 2? It didn't give us a picture for it, but it is, in fact, 1. And here, let me help you out in case you don't recognize those points. Dip, 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 dip. Dip, dip, dip. Dip, 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 dip. That looks like it is the function for sine x. In other words, if I take f of x being equal to the definite integral from 0 to x of cosine of t dt, it seems to make the function sine x. Now, as far as that goes, maybe it's not obvious that that's what it does, but in the second fundamental theorem of calculus, we'll be able to show that that is definitely what it does make, okay? Now, what the fundamental theorem of calculus, the first part, is supposed to do for us is let us take the derivative of this function. And when we do, we get f prime of x is equal to, how do I take the derivative of that? I don't have to. I'll just take the derivative of sine x. The derivative of sine x is cosine x. And notice that that, again, exactly matches up with our integral, or integrand, with just a change of variable. Right? That's what the fundamental theorem of calculus part 1 does for us. Shall we do another one? Probably. Example 2, evaluate the derivative with respect to x of this definite integral from 0 to x of the square root of t squared plus 1 dt. This is a fundamental theorem of calculus part 1 kind of question, and it's so easy to do. Remember that derivatives and integrals, they're inverses. They're going to cancel each other out, and the only thing that I have to do is switch my variable. I'm going to take this x, I'm going to plug it right in there. This is equal to x squared plus 1. What could be easier? That's it, it's done. All right, one that is maybe slightly, just tiny bit more challenging. I've got find the derivative of f of x is equal to the definite integral from pi over 2 to x cubed of cosine t dt. Now notice that essentially what we have here is a composite function because we have x cubed plugged into our kind of place where x was supposed to be, right? It's a composite function. And when you take the derivative of a composite function, you must remember to use the chain rule. Okay, yes. So f prime of x should be equal to, we're going to change our variable just like we did before, so it's cosine of x cubed, but we have ourselves a composite function, so also multiply it times the derivative of x cubed, which is 3x squared. And if you want to, of course, you can plug that or kind of push that towards the front. Okay, so here is then a chain rule version of the first fundamental theorem of calculus. Like I said, the chain rule version of it. If f is continuous on an open interval containing a, that's this a that's down here, and g of x is a differentiable function of x, that's our upper limit of integration here, then for every x in the interval, the derivative with respect to x of the definite integral from a to g of x of f of t dt is, now does that look familiar? Doesn't that just look like the chain rule? Because of course it is. We're going to take this g of x function, plug it in for the t, and then don't forget about the chain rule component. We'll multiply it times the derivative of g.